Let's get started. Now we've sorted out the technology. So welcome to my talk on functional big data. So yesterday I gave a talk on functional programming at the end of the day, which was map and flat map and reduce are your new best friends. And in a way, what this talk is about is really a continuation of that one, because it's actually the exact same ideas. Whereas yesterday I was talking about using functional programming to process collections, eliminate null pointer exceptions, and also a functional approach to concurrency. This is really those ideas, but applied to big collections of data, as in gigabytes spread across multiple machines on a cluster. And so the goal of the talk is really just to show that functional programming and big data work extremely well together. And in fact, if you look at the big data solutions that have been around for quite a while, they're basically functional programming. And the older ones didn't look quite as functional, but the newer technology like Spark, I mean, it's almost indistinguishable from regular collection processing code. So a little bit about me. So way back, I got my start programming in Lisp, which was, of course, one of those early functional programming languages. Lisp actually was invented back in 1958, believe it or not. And then later on, I ended up programming in Java, wrote the book Pojos in Action, which was all about Spring and Hibernate. And then started playing around with Amazon's Elastic Compute Cloud back in 2007, back in the very early days when it was very obscure. And I don't know if any of you saw the announcement, I think today, it's now a $6 billion business. AWS is now like a $6 billion business. So I just happened to be playing around with it in the very beginning. And I created a startup, Cloud Foundry, which got acquired by SpringSource right before SpringSource was acquired by VMware. And these days, I'm working on a startup and also doing some consulting. So, okay, so this is the agenda. So first, kind of an overview of sort of functional programming and data processing just to set the stage. Then I'm going to dive into 3 different big data technologies. Apache Hadoop, which is the original big data solution. Apache Spark, which is the much more modern approach to big data. And then also looking at Spark streaming very briefly, which is a great way of processing real-time data, processing it as it comes in. All right, so, it's funny, if you ever looked at the Hadoop examples, it's all about counting word frequencies in documents. And I'm just going to use the similar kinds of examples in this talk. So imagine that you were a Java developer, which probably many of you are, and you had to read a file and count the number of times each word occurs in that file. You'd probably write a bunch of code that looks like this, right? Where you open the file and you use like input stream reader, buffered reader, and so on, and then you define a result type, which in this case is a map from the words to the count of its occurrences, and then you return that at the end, and then you iterate through the lines in the file. And then you split each line into words, and then I uppercase the word just to just ignore case. And then I increment the corresponding entry in the hash map, incrementing it, creating it if necessary. So that's sort of the standard Java way of implementing something like word count, standard sort of typical iterative code. And so if you were to run it on a piece of text, like in this case, Gettysburg Address, and which says 407 years ago, you'd see that the word "the" appeared 11 times, "liberty" appeared once, and so on. So, okay, so I mean, that's code that we probably have written a lot recently, right? But the trouble is with this kind of code, it's pretty low level. Right? I mean, there was a lot of code there just to do something really simple. It's also very imperative, right? It's sort of kind of, you have to tell the computer how to do it as opposed to what you want accomplished. It's also quite verbose. And, there's a lot of mutable state there. And, that code was too complicated, but mutable variables in larger chunks of code can end up being somewhat error-prone. And then if you actually were given the job of running that in parallel on multiple cores or on multiple machines, how do you parallelize kind of for loops and the like? It sort of doesn't quite translate into the concurrent world easily. So the answer, of course, is to take a functional approach. And just to sort of summarize the big idea from my talk yesterday, functional programming is a paradigm where the building blocks of your code are functions, as opposed to object-oriented programming where you're building code out of, building programs out of objects or classes. And functional programming favors immutability. So immutable fields and also fields with fields and variables with final on them. And then it's a style of programming where you use what are known as higher order functions, which are functions that take other functions as parameters, and sometimes also return functions as a return value. And you're going to see a lot of higher order functions throughout this talk. And there's various benefits to functional programming. Number one, it's very concise and it's very expressive. And it turns out that it's also very easy to parallelize, which is really important in the big data world where you want to run things across clusters of machines. So what does the functional version look like? So here's the Scala version of the word count program. And it's only basically 4 lines. You read from the file, you translate you map lines to words, and then a couple of functions are used to count the frequencies of those words. So let's look at it and we'll return the same result. So let's look at it one line at a time. So the first thing you do is read from the file. And in Scala, it's super easy to just get an iterator of the lines in the file. It's possible that Java NIO has a better way of doing that as well. So the first thing you get is an iterator of strings, and those strings are actually lines. And then the next thing the code does is actually turn an iterator of lines into an iterator of words by using this flat map function. And what that is, that's actually a function that takes another function as an argument and applies that to each line. So we're basically splitting each line into words, and then it's concatenating the results together. And so you get back, and then if we turn it into a list, you actually get a list of words in the document. So we're just kind of a couple of function calls, we've already got the words. So if you look at flat map in pictures, you have an input of elements A, B, and so on. And a flat map is invoked on that passed in a function f, and it applies f to each of the input elements, which yields a sequence of values, and then all of those sequences are concatenated together. And there's a lot of other uses for flat map, as I talked about yesterday. And then the next thing you do is use group by. And group by basically groups together elements with the same key. And the key is determined, in this case, by applying the identity function to each of the input words. So it's basically what you get out is a map where the key is the word and the value is actually a collection of words, the occurrences of that word. So you can see that in maps to the list in, and so on. So here's group by in pictures. And so it applies the function f to each input element to yield a key, and then builds up a hash map from it. And then the final step is to actually map over the values in the hash map and apply the size function to each one. So basically turning the list of word occurrences into just an integer, and that gives you the word counts. So that's a very nice functional approach. And here's what map values or mapping in general does. So you've got some input elements, A, B, C, D, E. Map applies F to each one of those to give you FA, FB, FC, and so on. So that's functional programming kind of for doing, you know, what functional style word counts. So the question is, well, how do we scale this up to a cluster of machines? Perhaps we've got a massive amount of data that maybe is too big to sit on just one, to reside on one machine, or perhaps the operation that we want to perform on each of the documents is actually too computationally expensive to be done on a single machine, so we actually need to scale it out. So we're going to do we're going to have a clustered version of word count. So, you know, the standard technology for a long time for doing that was Apache Hadoop. And, you know, so just to describe that, Apache Hadoop is really this open source ecosystem for reliable, scalable, distributed computing. So it's actually kind of this whole family of different technologies that work together. And it gives you horizontal scaling on commodity hardware. So rather than having big, expensive boxes, you have a large number of smaller, much cheaper boxes. And instead of expensive SAN storage, for example, which is designed to be super reliable, you just have local storage on each of the machines. But if one of those disks fails, it's no big deal because you've replicated the data to other machines. So it's sort of cheap cluster computing on commodity hardware. So one key element of Hadoop, of course, is the Hadoop file system. And so it's a distributed file system. So you have a file which is comprised of blocks. And these blocks tend to be at least 64 megabytes in size. So we're talking kind of large files. And then those blocks are actually, well, the file is actually broken up into the blocks, and those blocks are distributed across data nodes and replicated as well. And then there's a name node that says, well, this file consists of these blocks which live on these machines. So that's HDFS, that's the storage technology. And then on top of that, of course, is MapReduce, which is the processing part of it. And it's basically a batch processing system. And it's provides all the plumbing for writing distributed jobs, and it takes care of farming the work out across the machines and also dealing with machine failure. So if a job is executing on a machine which then fails, Hadoop will just automatically restart that job on a different machine. And as the user, you're completely unaware of that. And so the MapReduce algorithm is pretty straightforward, and it actually is very functional in nature, as the name suggests, though the style in which you write it, the sort of the functional nature is somewhat obscured. But basically what it does, it treats the input data as a collection of key value pairs. So if you're reading from a file, you know, one way of interpreting a file is as a collection of lines, and where the offset in the file is the key, and the value is actually the line. And then all of the key value pairs are fed into mappers. So they're sort of doing it's kind of like the map function or the map values function that I described earlier. And for each input key value pair, the mapper outputs 0 or more new key value pairs. And then those key value pairs are shuffled by doing the equivalent of a group by. So in other words, the values with the same key are actually collected. And so for key value 1, you're going to have a list of values. For key value 2, you're going to have a list of values, and so on. And then those grouped together key values are then fed into a reducer, which actually combines the values and outputs another key value pair as the actual output data. So that's sort of a high-level view of the algorithm. And so you've got these mappers that are doing sort of a functional style of processing. And then you've got the reducers and the shuffle phase and the reducers, which are effectively doing a group by, and then kind of analogous to the mapping over the size function over the values. So here's a mapper for doing word count. And so the input to it, so map gets invoked with one of these key value pairs, And the input would be, for example, an offset in the file and a line, such as 4 and 7 years. And then it would output 4 and the value 1, score and the value 1, and the value 1. So it just outputs the individual words and a count as the key value pairs. And then there's the shuffling that happens. So for example, the would get output with a whole list of 1s, and that would get fed into a reducer, which in this case just sums up those 1s, and you get the and 11. So that's kind of how you could use how you could use a Hadoop to do word count. And then at a higher level, when you're actually using Hadoop, you're submitting jobs to the cluster, and a job consists of a mapper and a reducer, and then also the inputs and output paths, so which files in the file system to read and which files to write the output to. And then you tell it what the desired input and output formats are. And there's some other parameters that you can specify, such as the number of reducers. And by default, it will just pick some optimal number. And then when the job gets executed, the input format determines how many mappers get created. So typically, you have a file that consists of some number of blocks scattered around the cluster of machines. Hadoop will create a mapper on the machine that has that block. And so you get this parallelism across the cluster. So the mappers get run in parallel, the data then gets shuffled, and then fed into the reducers, and there's some number of reducers that are doing the reduction in parallel. So there's a bunch of benefits to using Hadoop, right? Like, it's sort of a simple programming abstraction. You write mappers, you write reducers, and yet you can build quite complex algorithms with it. And you can actually chain various map-reduce jobs together and do things like machine learning, Apache Hadoop, for example. But there's various downsides to using MapReduce. It's kind of verbose code, right? Like, if you compare the mapper and the reducer with the functional Scala version, one is like 4 lines of code. The others are like almost probably about 50 lines of code. It's very verbose, very kind of low level. Development can be challenging because you can't really unit test. Also, MapReduce is basically glorified disk-based batch processing, so it's actually really slow and high latency. It really is not real time. And also, it's a pretty rigid programming model as well. Everything has to be expressed in terms of a mapper and a reducer working together. There are some technologies around that try and make it a little easier. So, for example, here's an example of Scalding that is a Scala DSL for writing MapReduce jobs. And if you look at it, it's not that different from the Scala code that I described earlier. So that's quite good. It's nice and expressive, and it's also unit testable as well. So at some level, it actually improves the development experience. But what's actually happening under the covers is that all of this sort of, you express it in this functional, very concise functional way, but then it's all getting turned into a series of MapReduce jobs, and so which is slow and so on. So we can we actually need a better technology. And it turns out there is one. And that of course, is Apache Spark, which is kind of, becoming the way to do big data processing. In a way, Hadoop is like, kind of totally old school technology. And Apache Spark, was created not that long ago, I guess just a few years, at UC Berkeley in California. And it's sort of this generalized MapReduce functional data processing framework that actually does a lot of data processing in memory, so it can be orders of magnitude faster than Hadoop. It's written in Scala, but it's got APIs in Java and also Python. And the core abstraction in Spark is what's known as a resilient distributed data set, or an RDD. And what an RDD is basically, from a programming perspective, it's a collection of values. And if you actually look at the Scala, the actual API in Scala for RDDs, it looks just like the regular Scala collection API. They're basically indistinguishable. But what's actually happening under the covers is that these collections are actually partitioned across a cluster of machines. So when you perform an operation on one of these RDDs, it's actually being performed concurrently on all of the cores, on all of the machines in the cluster, so you get this massive parallelism. And so it ends up being very fast. Not only that, you can actually cache an RDD in memory. And so you can apply iterative algorithms to one of these cached RDDs, and they're basically happening at in-memory speed, as opposed to having to constantly read data in from storage. And that gives you a tremendous speed up. And also, these RDDs can be replicated. So not only are we partitioning them across the cluster, but they can actually be replicated as well for fault tolerance. So if one of the machines fails, its partitions can have actually already been replicated, can be used from a replica. So it sort of looks like this, right? So, so you create, to actually use Spark, you have to create what's known as a Spark context. And then you can read a file by calling Spark context.txt file, specifying a path. So in this case, I'm reading from an S3 bucket, but it could also be an HDFS file or even a local file. And so that will create so we end up with lines. That ends up being an RDD of strings, or which are the lines in the file. And that RDD gets partitioned across the nodes. So the file gets broken up into chunks, and each chunk is allocated to a particular machine. Then say when you apply some function to that RDD, that function ends up being, that the transformation gets performed in parallel across all of those machines, and it will create a new RDD that is also partitioned across the machines. And it's a very powerful programming model. And then, as I mentioned, normally an RDD is computed each time. So, so when you set up a pipeline and you sort of ask it to perform a computation, it will actually read from disk each time. But you can also just say cache this RDD and then run some iterative algorithm against it. And you get a big speed up. So here's the Spark version of word count. So you read in a file. So that gives you an RDD of lines. You flat map over it, turning the lines into words. Then you do a group by and a map values, and then you do a collector's map to turn the RDD back into a regular collection. But that code is basically identical to the Scala code. And so you've got this incredibly sort of expressive way of writing algorithms that just, it's very, very concise, unlike the traditional Hadoop MapReduce algorithms. And what's more, it's actually unit testable as well. So it's a much better development experience. So if we actually just kind of step through that code line by line, you can see what it does. So the text file method basically takes a file and gives you back an RDD of lines in that file, right? So that's kind of very much equivalent to the Scala code for reading a file. You get, except in this case, you get an RDD as opposed to an iterator. And then you flat map over it, which is applying a function to each line in the file, in this case, the split, invoking split on each line, to turn the RDD of lines into an RDD of words. And then there's the group by, that's collecting together elements with the same key, which in this case is actually collecting together the same words, and you end up with an RDD of tuples, where the first value in the tuple is the word, and the second value in the tuple is an iterable of those words. And then there's the map values that we saw before that's applying the size method to each of the iterable of words, and that gives us a tuple, an RDD of tuples of word and the word count. And then the final step is to turn that RDD into a map. So we've gone from the RDD world back into the regular collection world. And so in just sort of 4 short lines, we've done this distributed word count. And that could have actually scaled out to a whole cluster of machines. And you can write unit tests. So, this is just, regular JUnit test, and it's actually reading from just a local file in the file system. So very easy to work with. And then, in terms of how do we run jobs in this system, so you actually create an application jar that's got your processing code packaged up in it. And then that gets submitted to a driver program, which then works with a cluster manager to farm off the tasks to a whole set of worker nodes. So it just farms out the work to all of the machines in the cluster. And that just is done automatically on your behalf, and it's done in a fault-tolerant way. So you're you're mostly unaware that you're writing cluster code that's clustered. A little bit about the execution model. The actual computation is done lazily. So when you call text file to say load this file, it actually does not load the file at that point. It's basically just sort of creating metadata to say, here's an RDD that corresponds to this file. And then when you invoke methods that do transformations on RDDs, it doesn't actually do the work either. It just creates metadata saying this RDD is derived from that RDD by by mapping this function over it, for example. And it's only when you actually ask for the data by invoking an action method such as collect as map does any computation actually happen. So at that point, you've sort of built up this kind of DAG of RDDs, and you've said, give me the values. So Spark then kind of analyzes the DAG of RDDs, figures out what work needs to be done to compute the values, and then farms out a whole set of tasks to the machines on the cluster. So it's a pretty slick model. So, kind of like turning it into a real-world application. So this kind of mirrors some of the work that I've been doing. So imagine you have a banking application that's archiving all the sort of activity into an S3 bucket, right? So each file in the bucket contains multiple events, say in a JSON format, 1 event per line, right? And the event data is sort of like, this account was opened, this transfer for $200 succeeded, this transfer failed, etc. So you've got all these business events archived away in S3. And then with this, it's very straightforward to write some code that basically says, analyze all of that business activity and show you what has happened during a particular month, right? So for example, here I'm actually finding all of the log file data for the month of April, and then basically running code over it that's not too different from word count. And what we're getting back is a map saying there were so many of these business events, so many of this business event, and so on. And so it's a very, very tiny amount of code which actually could be processing a massive amount of data, depending on the size of the cluster. So that's kind of a high-level view of Spark. And as you can see, it's got a very, very functional API, so much so that you can't really tell the difference between regular collection processing and Spark processing. And Apache Sparks, you know, what I've described is the foundation of a really, really interesting ecosystem. So there's higher level libraries that have been built on top of Spark, like Spark SQL, that actually lets you query structured data in Spark and using SQL. There's also mlib, that's a machine learning library. So that's machine learning algorithms that have been implemented in terms of RDDs. And then there's GraphX, that's a graph computation engine as well. And these are all running on top of, so it's all this code is sitting on top of RDDs that are then partitioned and replicated across a cluster. And then another really interesting technology in the Spark ecosystem is Spark streaming that lets you process real-time streams of data. And that's what I'm going to talk about next. So, you know, sort of the standard way of doing data analytics is to store the data and then process it, right? You know, and that's kind of a nice, simple approach, but it sort of gives you, you know, there's kind of latency involved between, you know, there's a lag between data arriving in your system and then the data being analyzed and sort of reported on. You know, in the case of Hadoop, it's very, very high latency. In the case of Spark, you know, latency is less, but you know, you're not getting real-time results. So the solution is actually to analyze the data as it arrives, and you're basically running queries against the stream of input events and deriving insights in real time. And there's a bunch of different real-time streaming solutions out there. So like Apache Samza, Apache Storm, and then Spark streaming. And Spark streaming is really interesting because it's just built upon the underlying Apache Spark platform. So it can read data from a sort of arbitrary data sources. So out of the box, it supports Kafka and things like that. But you can actually plug in your own sources of streaming data. And then it can write data to HDFS, or it could write it to databases, or it could write it to sort of real-time dashboards. So you kind of have a real-time display of your data. And the core concept in Apache, in Spark streaming is what's called a D-stream, or a discretized stream. And what a D-stream actually is that Spark streaming takes the stream of input data and chops it up into little batches. So every second it could generate a new batch of data. And the actual batches are RDDs. So a D-stream looks like this. So a D-stream ends up being a sequence of RDDs. And so the first RDD is the data, say, from time 0 to time 1. The second RDD is from time 1 to time 2, and so on and so forth. And then you can apply sort of the operations that you can apply to a D-stream, like map and flat map and so on, actually get applied to the underlying RDDs. And so it lets you write code that looks like this. So this is a kind of a streaming version of word count. I'm going to kind of step through this line by line, but if you just kind of glance at it, it's got flat map, map, and reduce. And so it's kind of like not too different from the sort of the Spark streaming, from the original Spark version or from the original Scala version. So it's still very familiar, but in this case, we're actually operating on streams of data as it's arriving. So the first thing you do when you're programming Spark streaming is to create a streaming context. So it's kind of like the Spark context. But one of the critical parameters that you have to specify is the batch interval. So here it's saying create a new batch every second. So the data flows in and every second you kind of group the data together and output a new batch. And then once you've kind of set up the configuration, and then you have to specify a source of events. So in this case, I'm saying connect to this server on this port and just read the lines of text that are being output on that particular port. So if it was, and then so that what you then get back is a D stream of containing RDDs containing lines. So the first RDD would contain the first second of data or of lines. So it could have Mary had a little lamb. And then the second RDD would contain the input from t equals 1 to 2, and so on. And then you can apply operations like flat map on it, which actually get applied to the individual RDDs. So in this case, we're taking a D stream of lines and then flat mapping it to turning it into a D stream of words. And what's happening is the flat map is being applied to each of the RDDs as they're being produced. And then you kind of can map over the words in each RDD, outputting word and the number 1. So that's kind of actually using a similar algorithm that the Hadoop mapper used. So we'd get, so in the first RDD would have Mary 1, had 1, A1, little 1, and so on. And then the reduce by is actually doing the summing of the values by key. So it's kind of doing a combination of a group by and a map values to actually compute the word count. So now we've got RDDs of word counts flowing out of the system. So that's sort of a very quick overview of how D streams work. And the final thing, right, is once you've applied the transformations, you actually have to output them somehow. So one thing, for debugging, you can just call the print method, and that will just dump out, I think it's like the first 10 elements of each RDD. Or you can call save as, and there's various supported formats to just write those RDDs to file. So you could feed it into, so you could sort of analyze the real-time stream and then feed that data, save that data in S3 or in Hadoop, and then process it using SPARC. Or you can actually just iterate using for each RDD over each of the individual RDDs as they're being generated. And that could just send data to some arbitrary server, for example. So here's an example of that, which kind of mirrors some of the work I've been doing. So you've got a banking application that is publishing in real time the stream of events that represent the activity that's happening in the system. So money is getting transferred, accounts are being opened, and so on. And that could be published to some sort of message broker, for example. And we could actually analyze that in real time using SPARC streaming. So here's an example of some code that's actually, I wrote a custom receiver that's actually connecting to the server using some custom protocol and just outputting events as they arrive. And then you can analyze that, so for each sort of time interval, you get a summary of the activity within that time interval. Then one of the interesting things is that, well, if there was nothing happening within a particular time interval, it would be nice to have an event that kind of signified nothing happened in this time interval as opposed to the absence of an event. So I'm using the transform method on the D stream, which gets invoked with each RDD. And if the RDD does not contain any events, then I actually just make a new RDD that has just one event, the idle event. So now for each time interval, we're guaranteed of getting an RDD with either real events, with a summary of real events, or an idle event to say that nothing had happened. And then you can just do basic reporting on the activity by using the for each RDD method, and that will just tell you in each time interval what happened. And that could be used to update a real-time dashboard. So it's really, really simple. And then another kind of use case is, well, maybe you want to report on inactivity. You know, with some complex systems, you know, it can be hard to tell, you know, sort of diagnose problems, but one symptom of something being broken is the complete absence of events, right? You know, some part, some component died and events are no longer being emitted. And so with Spark streaming, it's actually quite straightforward to just analyze the stream of events to say, well, nothing actually really happened for the past 15 seconds. There must be something, perhaps something has broken. And that's just accomplished using this code. So what it's doing, it's actually it's applying the filter operation to just say, give me RDDs that are idle. And then I'm doing this sort of sliding window operation over it. And then for each RDD, I'm actually counting how many events happened within the idle events happened within the past 15 seconds. And if I actually see more than, well, 15 idle events, then I can tell that my system is now idle, and I can just generate an alert and trigger some diagnostic operation. So you can kind of you can sort of summarize real activity quite straightforwardly, and you can also detect inactivity in the system and trigger alarms. So that's pretty good. So that's my talk. So sort of in summary, right, you know, big data is essentially the killer app for functional programming. You know, there's been a huge interest in Scala which has been triggered by Apache Spark. Even though Spark can be used from Java and Python, it's actually Scala the fact that it's got a very nice Scala API has actually attracted a lot of people to Scala. So, you know, in a way, Hadoop is sort of the old school way of processing data. Apache Spark seems, you know, has many benefits. And then if you actually need to do real-time stream processing, Spark streaming is a great solution. So anyway, thank you, and I hope that you found this useful. And I guess that's the end of the conference.